everyone. Today we're going to be going over Birch reduction, how we make cyclohexadienes given benzene or some sort of aromatic compound, how we make isolated diene from that. So I just want to go through some basic hydrogenation that we've seen. If we were to take benzene, put it in an environment with hydrogen gas and give it a nickel catalyst, standard temperature and pressure, you're going to see no reaction. And I think this is pretty obvious, right? Because if we have benzene, we know that those pi electrons that are participating in that aromatic compound are very low in energy because of not only the resonance, but because of that delocalization. It's just very, very stable. Those electrons are free to run across 6 carbon atoms, very stable. If we wanted to hydrogenate a benzene though, what we could do is raise the atmospheric pressure extremely high and then use very high temperatures to achieve full hydrogenation. But this can be kind of challenging, right? Because how do you get 100 atmospheres easily? It's kind of hard in a lab. And if you want to avoid the headache, you can do what's called Birch reduction, and that's what we're going to be talking about today. When you treat it with sodium metal and methanol dissolved in ammonia, what you're going to get is this compound here. You're going to get an isolated diene in a ring, of course. Now, it's important to realize that you're not going to actually get the fully hydrogenated product here. What you can do from here is hydrogenate it more if you want to just get, like for example, if you wanted to make cyclohexane, you could just do hydrogenation from here and get that down even more. Okay, now that we looked at the reagents and why we do Birch reduction, I now want to get into the mechanism and how it actually does this. So when we look at our reagents, we have sodium, methanol, and ammonia. You'll notice here from my little drawn out mechanism that we actually don't use ammonia. Ammonia is just a way to help us dissolve both methanol and the sodium metal. Right, because if we dissolve sodium in water, you'll get an explosion. Right, and we don't want that. So you dissolve it in ammonia. So here's the mechanism. Sodium is going to donate one of its electrons. It's going to be like, hello, I'm going to attack any of the carbons. Granted, we don't have an electron donating or an electron withdrawing group. We'll get to that a little later. So sodium reaches out and donates one of its electrons. This pi bond here, for example, it could have been any of these. We could have attacked this carbon, that one, that one, that one. It's just happening to attack that one. So it attacks this carbon here, and it makes that pi bond homolytically cleave itself. Sorry, I have a little bit of a cold here, so it's kind of hard to lecture. So we get one pi electron going to that same attacked carbon, and we have another one going to this carbon-carbon sigma bond. Here in this pi bond, this kind of causes a chain reaction. This homolytically sleeves, we're going to combine an electron here to form a pi bond here on the sigma bond, and then this other electron is going to just be dumped onto a carbon absolutely as far away from the initially attacked carbon as possible. So what we get here, and I apologize for the rope thing, this pi bond remains undisturbed. We get a negative charge on that initial carbon. Remember, we coupled 2 electrons from the pi bonds respectively. We get a new pi bond, and we get a radical electron there. So you can notice here we have this compound. Now this is extremely unstable, and it's ready to react. So it looks at methanol, which is a protic solvent. The methanol here is going to donate a hydrogen. So I elaborated the bond here. The negative charge picks up the hydrogen and methanol. The O takes the electrons. Okay, so now we get this compound here. Well, now we have a radical on this side, right? So what we want to do is we want to do the exact same process again, just without all the fancy steps. Because there's no need to. We already have a radical, so the sodium donates an electron. And now we get another negative charge right here. Methanol comes right back, another equivalent, and is going to donate a hydrogen. All right, now we come over here and we have our final product. Isolated diene in a ring, of course. Now, it's important to understand that this is isolated, right? Which means it is reactive to the hydrogen gas and the metal catalyst that we've seen, right? Because now instead of having the aromaticity, having those electrons be conjugated and very stable, we're destabilizing them, and now this ring is subject to attack. Okay. Now I want to get into a little bit of a harder concept to understand. Even I can struggle with this sometimes, just getting right. So bear with me here. We have the effects of both an electron donating group and an electron withdrawing group. So to understand the effects of this, we have to understand this intermediate here that we looked at, right? So in the initial step, if we have an electron donating group, that's going to donate electron density towards the aromatic ring. So I just want you to imagine this thing is pushing electron density down. So I'm going to draw a dipole arrow, right? It's pushing electron density right into here. So if we were to take the hypothetical scenario here, and we had both an electron donating directly to this this carbon here or this carbon, well, which one would we expect? Well, we want to make the most stable product. Whenever you are deciding reactants, think the most stable product we can get. So if we look at this ring here, this electron donating group is donating electron density to a negative charge. That's going to raise the negative charge quite a lot. And it's going to actually make that more unstable. So this product is unstable, so we're not going to get this one. But if we look here at this one, we have an electron donating group on a double bond. Okay, and then we have a negative charge, right? So this is resonance stabilized, as we can see, but it also, because the electron donating group isn't affecting this negative charge here, it's actually more stable. All right, so that's electron donating groups. When you get to this part of the mechanism, you're going to see that this occurs here, and then of course you'll get your other one down there, your other electron. All right, moving on, we have electron withdrawing groups. So if we put an electron withdrawing groups, it's taking electron density away from the ring, from the aromatic ring. So we're actually going to see something opposite of what we saw in the last one. So an electron withdrawing group is going to draw electron density away from the ring. So if we have a negative charge on the carbon where there is an electron withdrawing group, what we're going to see is that negative charge is lowered in energy, right? Because that charge is being spread out by the electron withdrawing group. All right, so we would expect this one to form instead of this one, right? Because if the electron withdrawing group isn't in with this negative charge, then this negative charge compared to this one is higher in energy. So this one is higher in energy. And therefore less likely to form. So that's kind of the entire of Birch reduction. Hopefully you guys have a good grasp on this because it is a very important technique in lab that you'll see. I hope you guys enjoyed this video. If you have any questions, you will feel free to put them in the comments below. Thank you so much for watching. Have a wonderful day, guys.